Hi everyone, I'm Sam Pollard, and today I'll be talking about my digital assurance for high consequence systems late start LDRD. This is work I've been doing over the last 5 months or so with Shantai Repetian, and the title is Automated Error Analysis of Numerical Kernels for High Consequence Systems with Frama-C. Thanks again everyone for allowing me to put a video recording in, because I will not be able to attend the demo day. Now I want to talk about there's a lot of jargon in this title, and I want to go into it in a bit more detail. So I'll first start by giving an introduction to computer arithmetic, and computers can. Well, it starts with the theoretical limitation, which is computers can only approximate real numbers. This is because a number like pi has an infinite number of digits and a computer has a finite memory, but more practically, the most common approximation for real numbers is floating point, which use either typically 64 or 32 bits to represent a real number. This has been a tremendously successful abstraction, so much so that it is hard to buy a computer, other than maybe some small embedded systems that don't have floating point units. And computers are often measured by their floating point operations per second, or flops. However, floating point, because of its limited precision, can introduce error. So I want to give an example here to really drive the point home. So suppose you have in this, you're a spaceship flying around in a virtual space, and you see a 1 kilometer sphere at 1 kilometers away. Looks pretty accurate. You can see a little bit of relics or artifacts from how the graphics are rendered, but looks like a sphere. Now, suppose again that you got in a rocket ship and you flew 20,000 kilometers away, and then you looked at this sphere again from a telescope. It is now unrecognizable as a sphere, and this is because of floating point error. And you've reached the limit of the precision of your number. In this case, it's using 32 bits. To give an analogy to motivate this research further, if you were to buy any scientific instrument, any one worth purchasing, in this example, I have pipettes, you have a notion alongside its documentation of its accuracy and precision in various circumstances. In this case, how many microliters you're measuring. Now let's compare this to numerical software, which you almost never get this. You can sort of perhaps infer the precision by looking at the data type, the float here, but you can't get a notion of accuracy. And I want to change that. So the motivation for the digital assurance for high consequence systems mission campaign is that high consequence systems require scalable, generalizable verification tools so we can get the very high assurance that we need. The area I work in, which is called formal methods, can provide mathematical computer checked proofs of correctness, which means you can understand the entire state space of a program's behavior, provided you know provided you write the specifications correct and you put in the effort. However, formal methods is time consuming. Often it takes many times longer to write and prove the specifications in these proofs than it does to write the program in the first place. So to motivate this further, the goal of this project is to improve automation for formal methods, and in particular with floating point. So now I want to talk about how systems are specified in practice. One common way this is done is with ACSL, or the ANSI-C specification language. You might also hear this read as or pronounced as AXL. ACSL is a first-order logic about C programs. And the way it works is you write these specifications as special comments, and the C alongside ACSL is then fed into a tool called Frama-C, which generates verification conditions about that program's behavior. And these verification conditions can be typically solved by automated reasoning tools. So you can gain a lot of that automation and and have a computer do some of the work for you. Now, I'll give an example here, which is the most complex one I'm willing to put on a slide, which is swapping of two integers. Now, the specification requires that you can read to and write from, or read from and write to A and B, and that the variables at the end are in fact swapped. And it turns out this does verify in Frama-C, and so you can get more assurance that your implementation is correct. Of course, for industrial applications, these programs get a lot more complex. Now in practice, Frama-C is used at Sandia. We have several different projects using Frama-C in my department and others. Airbus uses Frama-C for verification of some of its aircraft software, as well as CEA List, which is the French Center for Atomic Energy, uses it. And I'll talk more about CEA List later. Now, if you recall, our goal is to improve automation for formal methods. Well, what about numerics? When we first started this project, we worked on linking floating point automated reasoning tools, of which there are a few, with Frama-C to try and gain this automation. However, beyond the implementation details, the fact that these automated reasoning tools speak kind of different languages than Frama-C, we quickly discovered that ACSL isn't quite expressive enough. And I'm not the first one to figure this out. There's been other work along this vein, namely out of NASA and I'm sure other places. So instead, what I decided to do is we decided that it was good to propose 5 features and kind of have a standardized language around which people can write these automated tools. And first, I'll talk about the 5 features. So the first 2 are required for error analysis, and the second 3 improve usability. So I'll just give the first 2 as an example. The first one, and I must say with a caveat, the first one does sort of in theory exist. The syntax is specified, but how exactly it behaves is implemented in the back end, sort of how these solvers actually solve this problem is not implemented. But to describe a little further, we have this notion of rounding error, which recall back to our example with pipettes, will have accuracy of this system. So we can actually get some analysis. And then the second one requires or provides this notion of compositionality. So suppose we have analysis, maybe some pen and paper analysis or some uncertainty perhaps from a sensor. For example, if you're measuring GPS, you might have some noise in the GPS measurement. These external notions of error must also be taken into account because otherwise your analysis might not be meaningful for the real world system under study. So these 2 provide error analysis and compositionality that, if implemented, would provide the automation that we need for verifying numerical systems with Frama-C. So I want to talk about some of the outcomes of this project. It was a kind of a short project, but I think that there were a couple really cool outcomes. The first one is this draft document to have a standard of ACSL language extensions that everyone can use and agree on. And I think a result of this was a really cool collaboration between Sandia, the French Center for Atomic Energy, CEA List, and NASA. Because as I was doing this work, I found out that both CEA List and NASA were all each developing, and as well as myself, we're all developing automated reasoning tools, and they all look slightly different. So we want to agree on this so we can kind of share our work. Another result of this was a collaborative publication that covers both work funded under the Advanced Simulation and Computing and work funded by this LDRD, and that will be published in the International Workshop on Numerical and Symbolic Abstract Domains. So for future work, I will publish a upcoming SAND report on more of the technical details. I didn't talk about what are these automated reasoning solvers look like. How does Frama-C translate into these things? I'll also plan to give an upcoming technical talk for a future multi-institutional community of practice. The software is in the process of being open sourced, should take a few more months. And then for future work, because this project is funded for the next 2 years as a 2-year LDRD, is to 1, agree on these ACSL features and scope the implementation effort with CEA List and NASA and other interested parties. If you're interested in being involved in this, please reach out to me. As well as linking automated reasoning tools with Frama-C so we can in fact get the automation, which was the goal of this project. I'll have more information at proof.sandia.gov, our departmental's webpage, for updates, and I'll leave the slide of references here for you to refer to. And that's all I have. Thanks, everyone.